Yesterday we were discussing Drude's model, Drude's model. So let me just remind you what we were discussing yesterday, give you a brief recap of the things that we did yesterday, and then we will, jump onto new topics. So yesterday I said that the Drude's model is based on some assumptions. You cannot justify all the assumptions, but these are assumptions that he made, and we have to understand what these assumptions are. So let me very briefly remind you what these assumptions were. So the assumptions are that the electrons, the free electrons, which are called conduction electrons, the conduction electrons, they constantly bombard against the immobile, impenetrable iron cores, right? That's what we discussed. So there are collisions that are happening, but between any two collisions, between the collisions, there is no force that acts on the electron. So there is no influence from the iron cores, even though they are positively charged and the electron is negatively charged. And there is no electron-electron repulsion also, right? So we neglect, not we, Drude, he neglected both these things, all right? So he said there is no electron-electron repulsion, there is no attraction between the electron and the iron core. And you know that there will be some attraction, but of course the impenetrability is still valid because the electron cannot penetrate into the atom, right, into the ionic core, because of the nature of forces that you have seen, that beyond a certain distance the force is too repulsive, right? You have seen the potential energy curve, the intramolecular forces or the atomic forces. So between the collisions, the electron moves, and in fact it's valid for all the electrons. The electrons move along a straight line path. And they move with a certain speed, with the speed v naught, which you can find from the kinetic theory, v naught. And this v naught is of the order of 10 to the power 7 centimeters per second. Right? You can get it from by equating half mv square to 3 halves kt. Right? The quick estimation of v naught. So that's one of the assumptions. The second assumption that he made was that once the collision has happened, once the electron has collided against the iron core, then what happens after that is, after the collision, the electron emerges along random directions. So there is no specific direction, or in other words, the probability, all directions are equally probable. So it can emerge in any direction, and there is no way to decide whether it will emerge in the forward direction or in the backward direction, right? So all directions are equally probable. So immediately after the collision, the direction that electron takes is arbitrary, or all the directions are equally probable. So maybe before the collision, the electron was traveling in the forward direction, and after the collision, it can be anywhere, you don't know. So what that means to say is that if you take a large number of electrons, the Avogadro's number of electrons, then the average momentum will be 0, isn't it? Because they are, after the collision, they're moving in all possible manners, right? And remember, all this is true when there is no force field. So this is in the absence of force field, all these assumptions. So some of these assumptions will get slightly modified once you will turn on the force field, right? So after the collision, the electron or the electrons, you know, move along the directions that are all equally probable. Along any direction actually, because all directions are equally probable. Any arbitrary direction. Why? Because all the directions are equally probable. And then the next was, he postulated a time, tau naught, which is called the relaxation time, which is the time between any two successive collisions, right? So this is the relaxation time. And it's the time between any two successive collisions, or you may also interpret it as dt over tau is a quantity that tells you how probable it is for an electron to undergo collision over the time interval dt, right? So the probability of electron colliding in the time interval dt, right? So that was the third. And the fourth one says that after the collision, the electron will emerge out at a speed which is directly proportional, or which is decided by the local temperature, the temperature at that point. So wherever it has undergone collision, wherever it has collided, it will come out with a speed, it will come out in arbitrary directions, but the speed that will come out is determined by the local temperature, the temperature of that place. And that is what it means by thermal equilibrium is attained through collisions. All right. So after the collision, the electron comes out. I mean, you can use a better language. Maybe comes out is not a good way to express it. Or maybe it bounces off the ionic core with a speed which is directly proportional to the local temperature. So if the temperature is more, the speed is going to be more, and this is this is one of the ways, or the way, in fact, in the Drude's model of attaining thermal equilibrium, comes out proportional to the speed, or proportional to the local temperature. By local, I mean the temperature in the vicinity of where the ion core is located. Local temperature. Okay. So with these assumptions, these four assumptions, we derived an equation that governs the dynamics of electron in the presence of a force field. So the equation that we derived, do you remember that? It's dp dt equals the force field minus p over tau, right? So In the absence of collisions, this term wouldn't be there, and the electron will go on accelerating forever because of the force field which is present, which could be the electric field or the magnetic field. And this term is then seen as a damping term that dampens the, or that opposes, or it's like akin to a viscosity, a viscous term that dampens the motion of electron. And in fact, in the last lecture, we took a very special case when the force field is time independent and it's just the electric field and it's just minus EE, right? And under that assumption, when you solve this equation, you found out that the electron is going to drift at a constant speed in the direction of the applied electric field, right? So this problem was solved, and the answer to this problem is that the electrons drift at a constant average speed V as opposed to V naught, right, along the direction of the applied electric field. Good. And you found, in fact, a relation. The relation that you found was V equals IR. Right? This is what you derived. And this current is because of this V, the drift velocity. Right? So, in fact, when we derived this relation, it was not in this form, but we recasted it in this form. The relation that we derived was J equals sigma E, or in vector form, we should write it like this, J equals sigma E. This is what we derived, and then you can write it in this form. And I wrote it in this form deliberately because of reasons that I will discuss now today. And we also obtained an expression for sigma. Right. Here sigma is the electrical conductivity. Right. So sigma is the electrical conductivity of the material, and the expression that we derived for sigma, which is same as 1 by rho, where rho is the resistivity, equals n E square tau by m, where n is the density of electrons, conduction electron density, E is the charge on electron, m is the mass of electron, and tau is the relaxation rate, the only phenomenological quantity in our model. Everything else can be known, right? So, can we know n? We can make a rough estimate of n. How would we make a rough estimate of n? For instance, let's take a specific case of sodium crystal. So, since we know its lattice structure, we know its lattice constant, or we can find that out using the X-ray diffraction technique. Once we know the lattice constant, we can find out the density of sodium, because we know the size of unit cell, we know the atomic mass of sodium. So, we can find the density, right, mass density. We can also find the number density, how many sodium atoms are present in a certain space, because we know the size of the unit cell, we know its crystal structure, so we know how many atoms reside within the unit cell, and we get the number of atoms per unit volume. Now, remember, we said in Drudet's model, and in fact it is true in general, that it is the valence electron that becomes conducting, that makes the conduction electron C. The core electron, they remain localized around the nucleus, right? So, that forms the ionic core. Okay. So, in the case of sodium, it is the 3s electron which becomes conducting, right, which becomes a part of the conduction C, right. So, therefore, there is exactly one electron that comes from sodium. So if you know how many sodium atoms are there in a unit volume, you know how many electrons are there in a unit volume, because each sodium atom gives out only one electron. On the other hand, if you are dealing with, let's say, let's take another case, copper. So in the case of copper, once again, there is one electron, that is the s electron, but this time it is the electron from the fourth shell, 4s electron, that is contributed to the conduction C, right? If we take the case of aluminum, in the case of aluminum, it is a p block element. So there are p electrons that are contributed to the conduction C, and you will have 3 electrons, right, per aluminum. Okay. If you take tin, there will be 4. If you take bismuth, there will be 5, and so on and so forth. So the point is that this is a quantity which you can easily estimate experimentally. Right? You can get an estimate of n for various metals. That's not easy. From the crystallographic data, you can mindful of the fact that the valence electrons contribute to the conduction C, you can estimate n. You know E, you know m. What do you measure in the lab? Do you measure sigma or do you measure rho? Which quantity do you measure in the lab? Sorry? You measure rho, right? And then you flip it and you get the reciprocal of rho is sigma. And how do you measure rho? The measurement of rho involves measurement of voltages and currents, right? So what you do is you take your specimen in the form of a bar of uniform cross section. So let's say it could be cylindrical, it could be rectangular, that's up to you. And sometimes it is dictated by what is available to you in the lab. So let's say this is your sample. Okay, so it has a uniform cross-sectional area. So what you do is you make a contact here on this face. So you let a current I flow through the sample. And how do you do that? All you need is a constant current source, right? And we experimentalists, we know how to design constant current source. We can have a source which gives a very robust constant current, and this current can be 1 amperes, 500 milliamperes, depending on the material, depending on the temperature, and so on and so forth. So a very fixed current, known current, measured very accurately. I mean, in current times, this is absolutely not a problem to pass a fixed current through a sample. You need a constant current source. And then what you do is you measure the voltage between any 2 points. So you make these contacts either by soldering wires on the sample surface, okay, or using a conducting paste, whatever. So you make these 2 contacts, and from here you take out the wires, conducting leads, and you connect them to a voltmeter, and that will read out the voltage. So you know the current, you know the voltage, you can immediately know the resistance, because the resistance is simply voltage divided by current. So once you know the resistance, you can get the resistivity, because resistance is nothing but rho times L divided by A. So if you know the quantity L, what is L? Length of? Not the length of the specimen, but the distance between the voltage probes, because this is what you're measuring here, right? This is the voltage that you're measuring. The voltage difference is measured between these 2 points and not between these 2 points, right? So this is your L. So you know L, you can measure the cross-sectional area of your sample. And you are measuring R from the experiment. You can measure L using a vernier caliper. You know, this distance could be few millimeters depending on the size of your sample. Your sample could be 1 centimeter long with 1 millimeter by 1 millimeter cross section, and then you put the voltage probes slightly away from the ends. So it could be, let's say, 5 millimeter. This is 1 millimeter by 1 millimeter square. You know the value of R. You can get rho. Take the reciprocal of it. You get sigma, right? So you get sigma, and therefore you can get tau, right? So why should we do all this? So to go to that, let's try to look at what we have, what is available to us, because right now my intent is to see how good is this with all these assumptions that we have made. And most of these assumptions are not justified, isn't it? It's very difficult to justify these assumptions or try to find out why it is the way it is. In fact, there are loopholes. For instance, I told you this velocity is not this, but it's in fact 2 orders of magnitude higher. But despite all this, Drude's model has lived with us for 1 century, right? And we may say some weaknesses of Drude's model, but we should not raise finger on Drude, Paul Drude, because when he designed this model, that was 1900. So how old is that? Or how recent is that? To get an estimate of that, you should understand that the electron was discovered in 1897. So it was just 3 years after the discovery of electron by J.J. Thomson. So you see that today we talk about hadrons and whatever. I mean, you talk about some high energy particles. How much time will it take to experimentally observe them or to use that knowledge to generate new knowledge? So here you see 1897, J.J. Thomson is telling that that a material has electrons in it. Before that, we didn't even know that the electrons exist. And in 1900, this fellow is giving you a theory of mobile electrons, okay? And he has some vague notion that there must be some centers against which the electrons is bouncing off. He had a very vague idea. That time the things were not as clear as they are today. So in hindsight, we may think that this is, why did he make these assumptions to begin with, but also recognize the time when he made these assumptions. So let's try to see how good is this result, because another reason why we should see how good this result is that even today, the first thing that we do is we compare our results, experimental results, to Drude's model, okay, for reasons that will become clearer as we go along. So let's try to look at some data. So here I will make a table. So we have a metal. Z is the valence electron count. So since Z is typically atomic number, so let's not confuse it with that. So let's name it something else. Let's call it NV, number of valence electrons. And N is the carrier concentration that you will get from NV and the crystallographic data. And rho is the measured electrical resistivity, and this is at 273 Kelvin. Now, why am I mentioning the temperature? Because the resistivity is a temperature dependent quantity. Okay, it changes with temperature. And this is measured in micro-ohm centimeter. Ohm is the unit of resistance, and from here you can work out the dimensions. And here is the tau that you will extract from these data. And tau is measured in seconds, and it's 10 to the power minus 14 seconds. Well, so let's take the example of sodium. What is the value of Nv? 1. What is the value of N? It's 2.65 into 10 to the power 28. So this N is in meter cube inverse, and it's 10 to the power 28 meter cube inverse. 2.65. Yeah. Or if you are dealing with let's do it in CGS units. If in CGS units it will be 22, and here will be centimeter, right? Because this is in CGS units, micro-ohm centimeter. So let's have it that way. So, the measured resistance, this is a measured quantity in the lab. This value for sodium is 4.2. 4.2 micro ohm centimeter at 273 Kelvin. Now, you have the formula, you can get tau, and the value of tau comes out to be 3.2. Now, you may say, well, what do we know about this tau? 3.2 into 10 to the power minus 14. That means 2 successive collisions happen as frequently as this, very, very fast, minus 14. But we have no reference. How do we know whether this is right or wrong? It could have come out to be minus 9 or minus 8, right? At this moment, we have no reference. We cannot comment on the accuracy of that result, right? But let's look at some more data. Copper. So, for copper, once again, it is 1. And this number is 8.47, which means that the copper has higher density. Its resistivity at low temperatures is 1.5. And for this fellow, tau turns out to be 2.7 in the same units. And let me, I mean, already something has emerged out, but let me just write one more example. Not one, but let's say so many examples. For gold, it's 1. For aluminum, it's 3. For tin, it's 4. You can then you can see that the density of course depends on the lattice parameter also. So, it may not scale directly with the numbers over here, but some correspondence would be seen. So, in this case, it is 5.86. For gold it is 5.9 actually, and aluminum 1.8. Aluminum is very light, and you may have used aluminum vessels, and then tin, that is 14.8. Now, tin has the highest carrier concentration of all these materials, right? Why? Because it's giving more electrons to the conduction band. Now, naively looking at this relation, you may think that that sigma for tin should be, because sigma scales with n, right? And E square is constant, m is constant. So, if tau doesn't vary much from one material to another material, then sigma should be highest for n, or rho should be lowest for tin. And in fact, the value of rho for tin is 10.6. which is not as per our expectations if we assume tau to be a constant quantity. For aluminum, it is 2.45. For what else is there? Gold. For gold, it is 2.04. And what about then you can work out the relaxation time, do the back calculation. So, for gold, the relaxation time is 3.0. For aluminum, it is 0.80, and for tin, it is 10.6. Right. Now, we can also estimate L. L is the mean free path, the distance electron travels between two successive collisions, scatterings, and that would be simply this time multiplied by which velocity? This velocity or this velocity? This one, because between the collisions, you remember this picture, between the collisions the electron is travelling with its thermal velocity. This is the average drift that it gets because of the force field. So, you have these ionic cores, so the electrons are moving very fast in the material, and are getting constantly bombarded against these. So it's moving like this. Like this it is moving, and you see it's moving along a straight line between the two collisions, and it is moving at a speed v naught between the two collisions if the temperature is uniform all through. Okay, so that's what it is doing, right? And some other electron might be moving in the opposite direction, so there's no net flow. But once you turn on the electric field, then what happens is things remain more or less the way they are, the way they were in the absence of the electric field. But you would see a very slow drift of this entire chaotic motion along the positive x-axis, because that's the direction you have applied the electric field. Remember this V, yesterday we estimated it. This V is of the order of 0.1 or 0.01 centimeters per second. So you are way down compared to the actual speed at which the electrons move. So they're jiggling, they're moving very fast back and forth, and constantly getting collided by the impenetrable iron cores. But if you turn on a force field, right, then there will be a slight drift of this whole cloud towards the positive x-axis, but at a very slow speed, right? So you can estimate the mean free path, and for all these, because you know the number tau, so let me just list a very average value of L by taking tau to be of the order of 10 to the power minus 14 seconds. If I take that, so it's varying from minus 14, 10 to the power minus 14 to less than 10 to the power minus 14. In fact, if you take, 14, I made a mistake in tau. I'm extremely sorry. you should have noticed it. I just copied this number again. This is not correct. So this is 0.23. 14. I mean, tau will be less 14, right? Because it has the highest resistivity. So that means the electrons are colliding very frequently, because collision is the source of, keeping the electrons from accelerating. All right. So if I take tau to be of the order of 10 to the power minus 14 to 10 to the power minus 15 seconds, and if I take V naught to be 10 to the power 7 centimeters per second, I can estimate L naught. Let's call it L naught, which is the mean free path, and L naught will be just tau times V naught, and this number will come out to be to vary between 1 angstrom to 10 angstrom. That is the distance that the electron travel before getting scattered. Now what have we learnt by drawing this table over here? So the first thing that we learnt is that the resistivity or the conductivity doesn't scale with n. It doesn't scale with n. So your n is large and yet your conductivity is small, right? Or in other words, there is something else, something besides the collision against the impenetrable iron cores which should be taken into account, right? So from here we learned that this collision source is not enough. Maybe there are other mechanisms because of which the collisions are happening. On the other hand, to favor Drude, we see that the distance traveled by an electron between any two events is roughly comparable to the lattice constant. The lattice constant A is of the order of 2 to 3 angstroms. So L naught comes out to be not very different from the lattice constant, right? And that supported the Drude's picture, Drude's idea that Okay, very roughly, the electrons are getting scattered by these ionic cores, because the distance that the electron travel between two successive scattering event collisions is approximately comparable to the lattice constant of your material. So we got two results from here. One result which very approximately, very hand wavingly says that yes, maybe very roughly this picture is correct. But this picture cannot be the only picture. This is not fully correct, because there are things that are completely disagreeing or not agreeing with this theory, right? Now, to get a better idea of the disagreement, what we are going to do is we are going to note down the values of rho at a still lower temperature. So, for instance, if you note down the values at 77 K, which is what is given in Ashcroft and Mermin, but in today's time you can measure the electrical resistivity of a material down to millikelvins, right? It's a routine work to measure resistivities down to 30 millikelvin. So but since we have data only for 77 millik, and we have data for lower temperatures also, but I didn't do much research. But even from this, things will become very, very clear, abundantly clear as what is wrong with Drury's model. So if we look at the relaxation time, the relaxation rate, this is the relaxation rate at 273 Kelvin. Now we are again looking at tau, but tau at 77 Kelvin, the relaxation rate at 77 Kelvin, and this number comes out to be 17. This number comes out to be 21. This number 3 has become 12. The number 0.8 has become 6.5. And the number 0.23 has become 1.1. So what do you see? You see an order of magnitude increase in tau naught. If tau naught will increase, V naught will not change much, because you haven't changed temperature much in going from 273 to 77. If you again use half mv square equal to 3 half kT, you will get the same order of magnitude for V naught. It's not that it will change by an order of magnitude, right? So you would see, so you will get L naughts, you will get mean free paths that are of the order of 1000 angstroms. That means an electron is not colliding until it travels approximately 1000 lattice spacings. Now this is clearly contradicting the Drury's model, because in Drury's model the electron is getting bombarded by the ionic cores every now and then, and there is no reason why it should not collide with an atomic core, ionic core, right, if it is there. So electrons somehow can bypass these ionic cores and travel as far as 1000 lattice spacings. Okay. In fact, if you go to even lower temperatures and if you prepare your material very carefully, then this can be as large as 10 to the power 8 lattice spacings. Now 10 to the power 8 is certainly huge, and in some cases it would just be the dimension of the material. This is called ballistic transport, where the electron sees only the boundaries of the material. So the material is so pure. So I'm in fact answering the question. So it's not just the ionic cores that are actually playing a role, but there is something else. And if you can take care of that something else, then your mean free paths get larger and larger. And in the phones that you use, there are devices which have very high mean free paths which are even 2 orders of magnitude higher than this. So you achieve that by preparing your material very carefully. But such large lattice spacings clearly show that the picture which is given by Drury is not the complete picture, right? It gives only a very rough idea. So So we can say that we can say that from these results that the electrons in a metal do not simply bounce off the ionic core, which is the main assumption that the Drude has made, as Drude has supposed. And we can, so this is one of the conclusions that we have drawn from these data by examining these data collected over several tens of years. And the other thing that we have come to is, so this inference we have made on the basis of this data, the low temperature data, right? Because if what Drude is saying is right at all temperatures, then this should not change, tau should not change, or L naught should not change. The other thing which we noticed is, if we compare at a given temperature, if we compare different materials, then we would see that things are not scaling simply with n, which means tau is not constant, which means tau is governed not just by scattering, by something else as well, right? So once again, the picture is not correct because tau is material dependent. It can be material dependent to some extent, because in some materials which are more densely packed, the lattice spacing can be a little smaller. So therefore, tau will be a bit smaller because the velocity is constant. But it clearly is, I mean, the variation in tau is clearly too large to be explained on the basis of lattice constants. So therefore, this tau is a material dependent quantity. It should be a material dependent quantity, but it is way beyond, you know, the dependency on material is way beyond what we expect from the Drude's model, and therefore this again points at the fallacy in Drude's model. So let me erase this and go to the next point. I shouldn't have erased this because I need it for the next one. So the next one is something that you are also familiar with, just as the electrical conductivity. So I will not spend too much time here, very, very quickly. So now we go to the case where in this equation, the force field, we have both the electric field as well as the magnetic field. In fact, we'll put a crossed electric and magnetic field, and this is the classic Hall effect experiment. So here is your material once again. This time it is more wide than thick. The thickness, let's say, is T, the width, let's say, is W, and the length, let's say, is L. And once again, we are passing a certain current through it. So the current I goes in, the current I comes out, and we have a magnetic field now in addition to the electric field. So where is the electric field, by the way? Where is the electric field in this picture? Did I apply the electric field? Huh? This is the electric field. You have connected it to a voltmeter, a voltage source, not voltmeter, sorry, a voltage source, a battery, right? So you have applied a voltage across these two faces, right? So you have applied, let's say, 1 volt, right? So therefore, the electric field will be V over L, where L is the length of the specimen, isn't it? That's the electric field. Okay, so you have crossed E field and B field. So in this case, you have an E field which is inside the material, which is in this direction. So since the current is traveling in this direction, the electrons are traveling in the opposite direction. This is the classic Hall experiment. So I will not delve time on it. You must have seen it in your 12th standard also. So I will directly write the results. So basically, the main point here is that you get a voltage because the electrons are moving in this direction, and there is a magnetic field. that magnetic field exerts a Lorentz force on the electrons. So the electrons are deflected towards the side faces and they start piling up there. Okay, so one of the faces will become more electron rich compared to the other face, and this will generate an electric field in the perpendicular direction, perpendicular to the electric field that you have applied from outside. And this electric field actually is called Hall field, right? And the corresponding voltage is called Hall voltage. And the experiment is, experimentally what you measure, which you measure even in the undergrad labs, I don't know if you guys did that experiment, that the Hall voltage at a fixed current I scales with the magnetic field, right? And the exact expression is okay, let me write not V but E. I mean okay, let me write V. And the V will come out to be I divided by N times T times B. This is for, I mean, you see, I have, I have taken a very nice geometry where the current is flowing, let's say, along positive y-axis, the magnetic field is along z-axis, the electrons will pile up along the face, which is perpendicular to the x-axis, and so the electric field will be, the Hall field will be along the x-axis. So I've made it into a fairly simpler case, the case that you actually deal with experimentally in the undergrad lab, and this is what you get, and this is the expression that you use. You say I is 10 milliamperes, N is the carrier concentration which you want to determine in your experiment, T is the thickness of your specimen, and B is the magnetic field that has been applied. So if you make a plot of V Hall versus voltage, you will get a straight line, and from the slope of that you can find the value of N, the carrier concentration, right? So V Hall versus B would look something like this, and you fit it to a straight line and you get the value of N, that is the carrier concentration. The sign of Hall voltage also tells you the sign of the carriers, right? This is what you do in a classic experiment on germanium chip, which could be N type or P type, right? You can, if you do equating the Lorentz force with the electrical force that will come about because of the generation of the perpendicular electric field. If you do it a little bit more formally with keeping all the vectors and everything, then what you are going to get is this, that the electric field Hall, which will again be along the x-axis, this will be RH. Okay, so since it will be along the x-axis, let me drop this, the vector sign, and then the current density J, and then the magnetic field B. Okay, so magnitude of B. If you want to put the vector, then you will put the x cap here. So this is the electric field. I have written it in this form. If you divide E Hall by this width, then you will get V Hall, right? So it's as simple as this. And what is RH? RH is known as the Hall coefficient. And this is nothing but 1 over NE, 1 over N times E. Oftentimes you will see a minus sign here because of charge of electron. So this is what RH is, nothing more than that. Now why did I do this? To show you the data. So let's see what the experimental results are, and and whether they are in good agreement with Drude's model or not. So from here you can see that 1 over NE times RH should be a quantity. If you take the if you look at 1 over, if you bring this down in the denominator, then this quantity should be equal to -1, right? That's what you expect. Okay. So let's see. So what we do is, now I'm going to plot the experimental data. Once again, you know, the full emphasis is on experiments. So here is your metal. At room temperature, what is the value of this quantity? Minus 1 over RH times N times E for various metals obtained experimentally. And this is how the experiment is done. You get N, so you plug in N here, you plug in E here, and you get the, you take this N from, once again, the calculated N, this N, and you take this RH from the measurements and electronic charge, you know. Is there any doubt? Did I confuse you? Did I clutter this thing a little bit? No. N is the carrier concentration that you would estimate from there. RH is the Hall coefficient that you would measure from here. You can say, what you're measuring in your experiment is basically this quantity. So this is the measured N, and that will give you RH. So we are trying to see whether it comes out to be 1 or not, right? This should come out to be 1 if everything is right. So what we get is, for lithium, this number is 0.8. For sodium, this number is 1.2, and they are fairly close to 1, because we expect this quantity to come out to be 1, isn't it? If you multiply it here, so your this quantity minus 1 over NERH should be equal to 1. Now remember what I'm doing. I'm taking RH from the experiment and N from the estimate and trying to see what we get here. So this is what we get. This is fine. For cesium, we get 0.9. All these metals have NV as 1. So that's very good. It works fairly nicely for them. But there are surprises. Now what are the surprises? The surprise is that if you perform the Hall measurement on aluminum, a very simple metal which is readily available as opposed to cesium, sodium and lithium. Sodium is also easily available, but you know, it is not very stable in air. But aluminum is, and you can do the measurements in lab. If you do Hall measurements on aluminum, you will be shocked. Why? Because this quantity comes out to be minus 0.3. Remember what I told you, it not only departs from 1 considerably, that is one of the issues. The other issue is that it carries an opposite sign. A sign that tells you that the majority carriers in aluminum are not electrons but holes. Now, of course, this is very difficult for you to envisage, that how come aluminum, which gives 3 electrons, not 1, not 2, but 3 electrons to the conduction band, has a Hall coefficient which is positive, which is a sign which is opposite to the sign that you expect from other metals, regular metals. And aluminum is not the only exception actually. You have magnesium, which gives 2 electrons, it is minus 0.4, which is once again negative. And you have then indium, which is also negative, and there are many others for which this quantity is negative, or in other words, the Hall coefficient is positive, or in other words, the carriers are positive. So how should we understand that? We cannot understand that within the framework of Druday's theory, right? So that's another problem. So this is about the Hall effect vis-a-vis the theory of Druday. Now the third part that I thought I will do today, and I see that we are already at 1 o'clock, is a very interesting part. So I will just I'll just tell you what I'm going to do in the next lecture, and we will do it in the next lecture. So in 5 minutes, I will tell what we are going to do. So in the next lecture, we will examine the behavior of a metal in the presence of light. Now this is something again you're not very unfamiliar with. You have seen metals and you see that the metals, they reflect light. Their reflectivity is rather high, right? You use silver for mirrors, the reflectance is very, very strong, right? So, the question we are going to ask is that given a piece of metal, you shine electromagnetic waves of frequencies omega, where omega can vary. You can take omega to be 0, in which case you are dealing with the DC conductivity, and you can have omega as high as 10 to the power 15, 16 or 17 hertz or radians per second. And the question that you would ask is, how are these waves going to react when they will see a piece of metal in their way? So, the light impinges on a metal, and then we are asking what will happen, whether this light will be reflected back or it will just pass through. Okay? This is the question that we will try to answer, or in other words, we will try to look at the dielectric constant epsilon of a metal, which is a function of omega and which is a complex quantity and a fairly complex in the true word of complexity also. And we will see that how a metal piece reacts or behaves in such a situation using Druday's model. All right, and you would see that Druday's model will do a fairly good job of explaining things when it comes to light falling on metal. And by the way, even here, the Druday's model did a fairly good, justification to the carrier concentration for various metals. But when it failed miserably. I mean, it not only gave a very small value for something that you expect to be 1, but also gave an opposite sign. I mean, this opposite sign is quite serious actually. I mean, you cannot simply understand it even if you tweak the Druday's model in this way or that way. And the aim of this lecture is to reach the point where you will start appreciating where aluminum has a sign which is different from that of lithium. Okay, but that will take time. We'll build that over a course of few lectures. So, next lecture will also be the last lecture on this model. I am already spending 2 lectures, I thought was more than enough. So, I have stopped now.